This is Jordan, the high school bully. He's a big guy with a mass of 60 kilograms. He's very hungry since it's lunch and he's looking for food.
Hey, give me my lunch money.
What the heck? Momentum is a vector quantity that measures the motion that an object has. In other words, it is a mass moving at a velocity. Momentum can be defined with the equation P equals mv. Let's find Jordan's momentum. We know that Jordan has a mass of 60 kilograms and that he is running at 5.6 meters per second. We write our given values down to keep track of them. It looks like we have all we need to find the momentum. All we do is plug in the values we have into P equals mv. Doing this, we get a value of 336 kilogram meters per second. Due to 2 sig figs being the least amount of sig figs when multiplying these values, the numbers has to be rounded to 340, which is also 2 sig figs.
Where the bins are.
Wait a minute!
The momentum in a closed, isolated system is conserved. In other words, the total momentum at the beginning equals the total momentum at the end. Conservation of momentum can be defined with the equation mva2 plus mvb2 equals mva1 plus mvb1. If in the video, Jordan accelerated from 5.6 meters per second to 8.3 meters per second, and Brian's velocity before the push was 5.3 meters per second, how can we calculate Brian's velocity after Jordan's push through this equation if Jordan slows down to 5.3 meters per second after the push and Brian has a mass of 50 kilograms? From the problem, we know the masses of both Brian and Jordan. We also know the initial velocity of both of them before the push. The question also gives us Jordan's velocity after the push. Now we plug in all our values watching the sig figs. Keep in mind the precision rule when adding or subtracting. Then we isolate the unknown variable, which is Brian's velocity after the push, and after all that, we end up with 9.2 meters per second.
They're running at fairly equal speeds. Jordan's thirst for hunger makes him run faster.
It's time to stop! It's time to stop, okay?
Impulse is defined as the rate of change in momentum. It also determines how much force is applied for how long. Impulse can be defined with the equation delta P equals mv2 minus mv1, or delta P equals F times delta T. After Jordan pushes Brian, he loses some speed, but he reaccelerates from 5.3 meters per second to 10 meters per second to catch up to Brian. What is Jordan's impulse? We know what Jordan's mass is from the description at the start of the video. After the push, Jordan is running at 5.3 meters per second, but we also know that he accelerates and that his final velocity is 10 meters per second. So we know our initial and final velocities. Next, we just plug in the values keeping in mind the different sig fig rules. We end up with 282 kilogram meters per second, but due to precision rule, the correct answer is 280 kilogram meters per second.
Don't hurt my friend!
An elastic collision is when two objects collide and go up separately. An elastic collision can be defined with the equation mva1 plus mvb1 equals mva2 plus mvb2. In an effort to help his friend, Kenny chucks a 0.2 kilogram ball at Jordan, who is running at 10 meters per second east. The ball is traveling at 14 meters per second west. What is Jordan's velocity if the ball is traveling 2 meters per second east after the collision? We know the masses of both Jordan and the ball and both their velocities before the collision. We also know the velocity of the ball after the collision. We plug in our values into the formula and again isolate the unknown variable, which is Jordan's velocity after the collision. We get an answer of 9.946667 meters per second, but after sig figs, we get 9.9 meters per second.
Oh, Jordan tackles him!
Hey! 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 Stop it! Stop it!
An inelastic collision is when objects collide and stick together. An inelastic collision can be defined by the equation mva1 plus mvb1 equals ma plus mb all times by v2. Jordan finally catches up to Brian and tackles him at 9.9 meters per second. Jordan is on Brian as they move forward and eventually topple onto the ground. If Brian was originally running at 9.2 meters per second, what is the velocity of both Jordan and Brian before they reach the ground? Again, we know both their masses. After the ball is thrown, Jordan slows down to 9.9 meters per second, which is the initial velocity before he tackles Brian. Brian is still running at 9.2 meters per second, which is the initial velocity before the tackle. We plug in our values into the formula. We isolate the unknown value, which is the velocity they are both moving at. The answer after these calculations are 9.58181 meters per second, which rounds to 9.6 meters per second because of sig figs. Since they are both now one big object, the velocities are the same for both Brian and Jordan after the tackle.